We're now going to study a series of examples of optimization problems. These are classic word problems in calculus. So the idea of an optimization problem is that we're looking for a maximum or a minimum of some quantity of interest, and the idea is we can control something, a distance, a position, a length, and we're trying to choose it to maximize or minimize some secondary property. And the hard part is most typically to interpret the actual desire or goal of the question and then build a function that would relate what we can control with what we're trying to optimize. So we'll look at this through a series of examples. All right. The classic fencing problems. All right. A farmer wants to build a rectangular enclosure to contain livestock. They've bought on sale 120 meters of wire fencing, and the nice side is that they're going to build this on the side of a barn. So we have a wall here, and what we're going to build out is some kind of fence like this. And of course, it doesn't have to be those dimensions. It could be something long and flat too, if that's advantageous. The goal here is, of course, to maximize the area. We have a limited perimeter, but we want to maximize the area enclosed. So our goal here is to maximize the area enclosed. Okay, what can we do with that? Well, what are the variables in this question and how are they related? Well, we have our wall, and if we think of the different kinds of fence layouts we can use, the real choice, if we're making it rectangular, is, let's call it the height here and the width here. How are these various things going to be related? Well, the area is pretty clearly width times height. So if we're looking down from above, the area enclosed is rectangular, width times height. And the other thing we're trying to keep constant is that the perimeter, or the fencing more precisely, is going to be 120 meters, and that 120 meters is going to be made up of these three segments. So it's going to be made up of an H plus a W plus another H, or 2H plus W. What that means is that we can't choose H to be 100 and W to be 100 both at the same time. We would run out of fence if we did that. So there's some relationship between these. If I pick the height, then the width has to come along for the ride to keep this 120 meters valid. Knowing that these two equations are playing a role at the same time, and we want the area to be maximized, let's call that A here. Then we can isolate here for, let's say, W. So W will always be 120 minus 2H, because if I choose the height, then I know what width of material I have left, or length of fencing I have left for that side. And that means that our area, which is W times H, can be simplified into the single variable function 120 minus 2H times H. Now, what's the natural domain? Well, you can get a little fussy. H greater than 0, let's say greater than equal to 0. We could make a 0 length fence if we wanted. And from the scenario, the tallest we can make this fence would be 60 meters on one side and then 0 width and then going back. So H is going to be less than or equal to 60 as well. Those are the only reasonable values we can think of for the length of this side of the fencing. Okay. So now we're going to maximize this function on this domain and try to make an argument about why the point we find is a global maximum. All right. So our area is given by 120 minus 2H times H, which is, I'm going to expand it because we're going to differentiate in a second, and it's easier to differentiate it like this. And what we're going to look for are the critical points of the area. And for that, we're going to do A prime, or I'm going to put it more technically here for a second, dA dH, or A prime. and that will be 120 minus 4h. Set that equal to 0. So 0 is equal to our 120 minus 4h. 4h equals 120, and h equals 30 meters. Okay. So that is the only critical point for the function a. Okay, so that's our critical point. Let's take it. We could do first derivative tests, we could do second derivative tests, but we actually have a nice limited domain. So what we can do is say that the global max area, global max of A, let's write it that way, is going to occur at a critical point or at an endpoint. And that's, our critical point was h equals 30. Our two endpoints were h equals 0 and 60. How do we know which one gives us the highest value? Our intuition certainly tells us that a fence with 0 width or 0 height is not going to give us much, but we can validate that mathematically by comparing the a values for those three different numbers. So we're going to compare a with 0 height, a with 30, and a with 60. And remember, here's our formula up here for area. Area of 0 is, well, we're multiplying by 0, so it's 0. A of 30 is going to be the more interesting one. We'll have 120 minus 60 times 30, and that is going to equal 1,800 square meters. That's square meters too. And A of 60 is going to be equal to 120 minus 2 times 60. That's also 0. So by comparing these three values here, A of 0 at the endpoint, A of 30 at the critical point, and A of 60, we can conclude that we have a global maximum at x equals, or at h equals 30. So because we're on closed interval with 0 less than equal to h less than equal to 60, and h area of 30, and h equals, let's say there, h equals 30 gives the largest area out of all the critical points and endpoints. H equals 30, area equals 1,800 square meters is the global max of the possible area, possible enclosure area. And it might behoove us to find the total dimensions. I believe the question asked for that, but our width is 120 minus 2h, so it would be 60. So the fencing area we're talking about uses a little bit of h and twice as much width, 30, 30, and 60 across here. That would be our optimal zone or enclosed space given the 120 meter restriction on the fencing length.